Okay, so I want you to think about this triangular prism, and we want to know what the net flux through the enclosed surface is. And as you can see down the bottom left, there is a constant electric field that's horizontal to the table, and it passes right through this, this enclosed surface. This is something that we're going to do a lot of, is talking about the net flux through an enclosed surface. So let's remind ourselves what flux is. So flux is the electric field dot the area. And so when we talk about that dot product, we're really talking about a projection. And the best way to think about it is you get maximal flux, so E times A, when, so here's a nice little graphic that I found. It's really hard to draw stuff in perspective. So you can see when the electric field is going, just totally straight through, then you have maximal flux. So when we talk about the dot product, though, let me grab a color. Let's do green. We're talking about the electric field. So here's the electric field that's right there. But when we're talking about what does the vector area mean, it is the vector that is normal to the area, okay? And so that is your area vector. So you see that E dot A here, right, that the angle is 0, and so it's EA cosine 0, so it's just EA, so that's maximal. So just reminding you, that's how we define our area vector. Okay, so to calculate the net flux through this enclosed surface, we can just calculate the flux through each of the areas, each of the individual areas. So let's start with the bottom. So we're looking at the bottom right here. So if I draw a side view, so there's the bottom, and just for reference, that's length B right there. There is an electric field that is in that direction. And when we talk about flux, we want to know it's E dot A. Well, what is the A vector? Well, the A vector is going to be normal to the surface and always points out. Okay, so that's just a convention that we have, is that the area vector always points out. So E is perpendicular to A here. So that means that the flux through the bottom is 0. And hopefully, as you're getting a feeling for flux, you had that intuition already. Okay. All right. The next thing I want to look at are the front and back triangles. So let's draw that. So here's surface 3. Here's surface 4. This is the front, and that's the back. So again, for reference, our electric field is coming this way for both of them. That's an A, that's a B, that's a C. Right, so just sort of seeing where you are right here. So if this is if this triangle is my area, what is my area vector? Well, it's normal. So that means normal means it's either in or out of into or out of the page. For the front, it's going to be out of the page because it's normal and it points out from the surface. And for the back, out from the surface is going to look like that. But either way, in both of these situations, again, E is perpendicular to A, and therefore phi 3 and phi 4 are 0. So far, we've only found 0 things. We've done the bottom, and we've done those. So maybe we'll find something with a non-zero flux. All right, I want to look at the back now. So that's one. So if we look at the side view, right? And we have our electric field is going like this. Okay, now I think we're getting somewhere, right? So what does our area vector look like? Our area vector, I'll draw it in red so it's associated with the area. It's perpendicular to this area, so it's either to the left or right here. But what do we know? It has to go out, right? Out from the surface. So there's our area vector. So phi sub 1 E dot A, ooh, that is going to be negative, right? If E dot A here is going to give you a cosine of 180, so it's a negative 1. So it's negative E times, and then what's the area of this rectangle? Well, we see this has the dimension little a, and this has the dimension w. So it's going to be E times A times W. And of course it is negative because the flux is going into the surface. Okay, so the fact that we define A to be out says that any flux going into a surface is going to be negative. Flux going out of a surface is going to be positive. So finally, that brings us to the very exciting slope. So let's draw that. So there's the sloped thing, all right? And our electric field is that direction. Let's draw our A vector. Our A vector is going to be like that. So when we write phi 2 is E dot A, we're doing EA cosine theta, oopsies, where that is the theta. So we got to do a little bit of fun geometry. So let me get another color so I can just sort of sketch out some things. Okay, so this triangle, I'll just ignore that never happened. This triangle looks like this. This was A, this was B, that was C. So remember with E dot A, we're really looking at this projection, right? This is sort of A parallel, if you will, right? So phi is E times that projection of the A onto there. Okay, so what triangle is that, right? So there's our 90-degree angle. There's a hypotenuse. Okay, so this is just fun with triangles now. All right, so this has to be a 90-degree angle. So that's 90 minus theta, right? That's 90-degree angle because by definition the area vector was normal to the area. So that's 90 minus theta. So we've got this guy, and so that means that is 90 minus theta, which means that is theta. Woohoo! So EA cosine theta, wow, glad I wrote that over again. What is cosine theta? My gosh. There we go. Cosine theta is adjacent over hypotenuse. So it's A over C. All right. And what is our actual area of, so now I'm writing in red, that's confusing, but here we are. This is the slope. What is that area of that rectangle? It's C times W. So, boom, E, A, W. All right, we're almost there, guys. So, net flux is phi 1 plus phi 2 plus phi 3 plus phi 4 plus phi 5. All right, negative EAW, and that was EAW, and then that was 0, 0, 0. And guess what? Haha, it's still 0. Whee! Okay, so the important thing is that the net flux through an enclosed surface that contains no charge is 0.